In the previous video, we reached to this structural instantiation of the bounds and square root, and we used clock 50, but we changed its frequency to be at the same pace as our circuit, our square root calculator. And we found that a clock frequency of 40 megahertz is suitable for our design. Now, we need to add a phase-locked loop component to generate that clock frequency for us. Changing this clock in the SDC file to another number, another frequency, doesn't actually change the hardware. In order to generate a clock with 40 megahertz, you actually need to either divide the clock frequency, if possible. If your input frequency, for example, is 80 megahertz, you can divide it by 2 by using a 1-bit counter, and then take the output or take the first bit of the counter to be your clock, to be your 40 megahertz clock. However, we are going from 50 megahertz to 40 megahertz, so division is not an option here. What we need to use is the more generic component, which is phased or phase-locked loop component, which is used to basically regulate the clock signal to the value that we want. And the easiest way to add this component is through the IP catalog. I think I'm going to use this IP catalog right now. I don't want you to. I don't want to go over the what we call platform designer at the moment. Maybe later in a later video when we want to integrate the hard processor system. But right now we don't need that actually. All you need is to search for PLL. Okay? PLL. Just type PLL here, and you will get a number of components, and pick this component, which is PLL Intel FPGA IP. By the way, maybe you've noticed the difference in the user interface. I have downgraded my Quartus Prime from version 23.1 to version 18.1 because latest version right now is 23.1. I don't want to have any chances of instability. So I just downgraded so that once we implement the code, we're at least highly confident that the design should work, okay? Hopefully without bugs. Okay, so double click on this, double click on the PLL Intel FPGA IP, and then give it a name. You can call it any name. Let's say PLL 0. Okay, and select Verilog since we are using Verilog. And then the Mega Wizard will start, which is basically nothing but an interface to take the parameters for your PLL. Okay, so the first one is integer. So let's leave it as at integer. I believe using the fractional, I'm not sure, but it may require a license. Okay, so let's have the free version, okay, of PLL. And our input or reference clock is actually the clock 50, will be clock 50, which is running at 50 megahertz, not 100 megahertz. Okay, leave the rest as is, but the output clock now, instead of 100, we want to generate 40. And make sure that the actual frequency now is changed to actually 40 exactly, or almost 40 at least. Notice that this may not be the case. If you want, for example, to generate a 1 megahertz. 1 megahertz will not be generated exactly as 1 megahertz. This is the actual frequency that you may get if you try to generate a 1 megahertz frequency out of 50 megahertz frequency. But luckily for us, 40 is actually can be generated, okay, as is, and then the phase shift will be 0 for us, and the duty cycle will be also 50%. So click finish. No need to go over the other tabs. And clicking finish will generate the Verilog code for this PLL. And then you just need to instantiate it to use it. So the plan is to take clock 50 and feed it to the PLL, and the PLL will generate for us the clock 40. Okay, so this is finished now. Generation is finished. Once you click exit, the GUI will ask you to add, so you must add this QIP, okay, Quartus IP, in order to be able to use it. So add this, and then you'll add two actually components. This one is for synthesis, and this one is for simulation. Okay, you want to simulate the PLL, you'll use the SIP. Okay, I'm not going to show you how to simulate it, but at least maybe in the future, I don't know. But for now, I'm going to use it for implementation. So we want to be more organized a little bit. So let me create a wire called clock 40 to hold the 40 megahertz for us. Okay. Also, I want to have one reset for the circuit and another reset for the PLL. Okay, because why? Because I don't want the circuit to start while the PLL is not locked. And so the PLL, remember, the PLL is having a locked component or locked output, I'm sorry, locked output. So once locked, at the beginning, locked will be 0. Okay, and then once locked is 1, we know that the output clock is following the frequency that you asked for. Okay, so we will be having two. This is one way of doing it, by the way. There are other ways, but I'm using this way for simplicity. So I'm going to have key 0 for the circuit reset, and then key 1 for the PLL reset. So in order to actually instantiate the PLL, go to the PLL0.v, and then here, this is just shown for your convenience, okay? You can copy this. This is just an instantiation of the PLL here, okay? But I'm going to copy this just just in case something is different here. I don't think that something is different, but just in case. So I'm going to actually paste this and then give it a name, PLL 01, for example, okay? And bind the parameter, the ports by name, okay? I'm going to give the ports the signal which you so the reference clock is clock 50, and my reset is going to be this is an active high reset, I believe. I just check that. Let me open up the component here. Okay. Yeah, it looks like it is an active high reset. Okay, active high reset. we can get back to the documentation if we need to, but let's just assume that it is an active high reset. So for this, if you want to connect it to key one is active low, so we need to invert it. Okay, we need to invert it in order to be active high. All right. Now this is my actually clock 40. Clock 40. This is the wire that I just created up. And also, I want to create another wire called locked, just for fun. Okay, locked is connected to locked. Okay, you don't have to do that. If you don't want to connect it to anything, you just do this. Okay, but I'm going to connect it to locked, although I'm out of any LEDs, so I cannot actually display locked. Once this is done, okay, one more thing that you probably need to do, just make sure that you go to assignments and then in device, okay, and then device pin options, go to unused pins here and make sure that you select this option here, which is as input tri-stated, okay? I think the default is one of these, but it's not good. The default is not good. The LED, if it is not connected, it is going to be half lit. Okay, so you don't want that. You want it to be either on or off, and this is the option for that. Okay, so once this is done, we need to change this clock now to clock 40, yeah, because we want our circuit to work. Clock 40, okay, and that's it for the hardware, okay? I mean the Verilog part. Now, in the next video, I'm going to compile this. I'm going to actually compile the design, and then in the next video, I'm going to show you a demo, simple demo. Let's calculate the square root of something using this simple and very inaccurate square root calculator, okay? But the point is just to show you practical stuff. So see you in the next video. You don't have to be here for the compilation. I'll just compile and then try to take pictures using my mobile phone, okay? And then show you the video in the next, show you the result in the next video.